first part of this course, which is the combinatorics part, which is really, combinatorics is the art of counting things. And by counting things, I mean figuring out the sizes of certain sets. So why is this an interesting thing? So it sounds very mathematical, and it is. But it's also something that happens incredibly often in computer science. So many of the things that we'll study as computer scientists really boil down to the sizes of certain sets. And sort of the easiest sort of examples of these things are when you consider optimization problems. So you may have heard of the traveling salesman problem before, or the minimum matching problem, or any number of these sort of famous problems that are optimization problems that basically they happen when there's a whole space of solutions, possible solutions to a problem. So there's all the different ways in which a traveling salesman can visit the cities that he has to sell things in. And your job is to find the very best one of those things. And so what does that have to do with the size of sets? Well, in those examples, the set is the space of possible solutions. So every possible solution is an element of that set. And the first thing you should try when you have one of these problems to solve, or you confront one of these problems, is to say, does the easy solution work? And what's the easy solution for one of these things? Well, if I want to know what is the best traveling salesman tour, what's the shortest traveling salesman tour, I can just list out all of the possible traveling salesman tours, measure how long each one is, and then take the best one. Now, is that an efficient algorithm? Well, that depends how many tours there are. And how many tours are there? Well, that's exactly the size of this set, which is, the set contains one element per tour. So all the time, we will be, if you work at all with algorithms or even efficient implementations, you're estimating the sizes of sets to determine whether this code that you just wrote is efficient, whether it's going to run in a second or two, or whether it's going to take weeks or years to run. So that's basically the first part of the course. And today we're going to focus on two particular let's say, rules. And these are, or the first one is what we call the product rule, or the product principle. And I'll state it sort of semi-formally, which we can do the following way. Suppose we have a procedure to perform that has so there's m steps involved in this procedure. So maybe it's making a recipe, or whatever, or an algorithm, or something. And for each I in 1 through m, so for each step, there are n sub I different ways to perform step I. Okay? So there's m different steps that we need to do to complete this procedure. And there's, for the ith step, there's this many different ways to perform it. Then, let me add a little caveat. And this is true no no matter how we performed steps, all the previous steps, 1 up to I minus 1. Okay? So it doesn't matter what I did before this, at the ith step, there's exactly n sub I ways to perform this. Then the total number of ways to perform the procedure is n1 times n2 times n3 all the way up to nm. So the first number of ways of doing the first step times the number of ways of doing the second step times the number of ways of doing the third step all the way up to the number of ways of doing the last step. Okay? So that's the statement of this thing. And I'll put a little side note here because we're going to use it sometimes, that we have a shorthand for these things because in combinatorics, when you're counting things, and really because of the product rule, it happens a lot that you get these products that have, you know, term 1, term 2, term 3, term 4, or factor 1, factor 2, factor 3, factor 4, and so on. And so there's a notation for that, and it looks like this. So this is just like the notation for sums, the sigma notation that you've seen before, except instead of putting a plus sign in between each of these things, you put a multiplication sign. Okay. All right, so here's a baby example. How many strings are there where, let's say, 2-letter strings where the first, let's say, 2-character strings, let's be really specific, where the first character is an uppercase English letter the second character is a digit, and that's decimal digit 0, 1, 2, 3, up to 9. Okay? So let's say somebody is designing a security system and they say you need a password, and we're very strict about passwords. We want to be secure, so we only accept passwords of this type. So the first thing you should say as a computer scientist is, well, how secure is this really? Because a very common attack for passwords is the brute force attack, which is, let's just try every possible password. In that case, you'd like to know how many possible passwords there are. So would anybody like to shout out the answer? 260. 260. Okay. Why 260?
Because the product rule is 26 possible uppercase English letters.
Yeah.
10 possible.
Yeah. So I'll describe a procedure to write one of these strings. Step 1 is choose an uppercase English letter. How many ways are there to choose an uppercase English letter? 26 ways. There's 26 English letters. Step 2 is choose a digit. How many ways are there to do that? There's n2 ways, which is 10. Any one of these 10 digits here. So by the product rule, the answer is N1 times N2 is 26 times 10 is 260. Okay. So not a particularly secure mechanism for, let's say, passwords. For a variety of reasons. So there may be other things on top of this, like if you enter the wrong password 3 times, then the whole device explodes or something. That would make it a little more secure. But even for like a high security application, even being able to just pick a random one and guess that means the probability that you got it is 1 out of 260. That's not a particularly small probability, right? I mean, depends what's at stake here, but you know, if this is the password for the American nuclear arsenal, then I don't want someone to be able to guess that with probability even 1 out of 260. Okay. So there's the sort of the first baby example. Next example. The number of n-bit binary strings. So just to be really clear, here's what I mean. If I take n equals 3, the strings that I'm considering are strings of length 3 over the alphabet 0, 1. And there's 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay. So the answer for n equals 3 is 8. So can someone, if we want to use the product rule to answer this in general, can someone describe a procedure for generating these things? Yeah. So 2 to the power n is the answer. And so why is that? Describe it in terms of this product rule language. If I'm going to write one of these strings, yep.
In each step, there's 2 possibilities, 2 ways to perform the step. 2 times 2 times 2 is just 2 to the n.
Yeah, yeah. So we'll say, you know, here's the procedure for writing one of these things. To write an n-bit binary string, b1 through bn. We'll say for I equals 1 up to n, choose the value of bi. So that's a value that's either 0 or 1. And so this is a procedure that has n steps in it. And for each step, there's 2 choices. I can write a 0 or I can write a 1. So ni is equal to 2 binary strings is n1 times n2 times n3 and so on up to nn, which is 2 times 2 times 2 times 2. The number of factors in here is n, and we have a shorthand for that. That's 2 to the power n. Okay? So is that clear? No big surprises here, but obviously a fairly important question for computer scientists, since everything in modern computers, at least, is represented as binary strings. So this, for example, tells us when we talk about a 32-bit or a 64-bit computer, this tells us the size of the largest integer that we can represent in 32 bits or 64 bits. All right. So questions so far? Everything is clear? All right. So let's move on to something a little more abstract. So let's start with two sets. A is a set of size M. B is a set of size N. How many functions from A onto B are there? So what does that even mean? Well, does anybody remember the definition of a function, either formally or informally? So, yep.
Something that takes an input and gives an output.
Yeah. So you can think of it as something that takes an input of a particular type and returns an output of a particular type. So this notation here says the input to the function will be an element of the set A, and the output of the function will be an element of the set B. And if you go back to 1805 and you guys talked about relations, function is a particular kind of relation, and what's special about it, so the relation between pairs, one in A, one in B, and what's special about it is that each element in A appears exactly once. So there's a sort of reasonable picture of this where, let's say, this is A, and there's 4 elements in A. Let's call them A, B, C, D, and here's B. And let's put 6 elements in B. And we'll call those elements 1, 2, 3, 4, 5, 6. And the standard way of denoting one of these functions is to use arrows. So each element in A has one arrow coming out of it that points to an element in B. So for example, maybe f of A is 4. F of B is 2. F of C is 4. And f of D maybe is 6. So we can write this down. Longhand, f of A is 4. F of B is 2. F of C is 4, and f of D is 6. Now that's not the only possible function from A to B. That's just one of the many, many functions from A to B that exist. This is just one particular function. And I want to know how many functions are there? Yep. Yep. Well, what's vertical and what's horizontal? So I don't want to spend too much time on this because it doesn't totally apply. A, B, C, D. So there's the x-axis, and here's the y-axis. 1, 2, 3, 4, 5, 6. And if you plot this, then what you see is A, 4, B, 2, C, 4, D, 6. So up here. So it passes the vertical line test. Any vertical line only intersects one thing. I think you mean it doesn't pass the horizontal line test, but lots of functions don't, right? Only increasing and decreasing ones don't. Only increasing or decreasing ones do pass the test. Okay? Okay, so let's maybe change the notation a little bit. And instead of calling these A, B, C, D, let's call these A1, A2, A3, and A4. So this is A1, A2, A3, and A4. So can you think of a procedure? Can you describe a procedure for me for creating one of these functions? Yeah? Exactly. So in terms of a procedure, so the answer is n to the m, and that's because of the following procedure for I equals. So now we're calling A, we'll give its elements names, A1, A2, up to AM. And here's the procedure for I equals 1 to M. Choose a value in, let's call it value BI in B, and set F of AI equal to that value you just chose. Sort of like I did here. F of A1, I need to pick a value for that, I'll pick 4. F of A2, I need to pick a value for that, I'll pick 2. F of A3, I'll pick 4. F of A4, I'll pick 6. Okay? So, this is a procedure with M steps. And for each step, the ith step, I have that the number of options is the size of B, and that's of size n by definition. So the answer, how many functions are there from A to B, is n1, this is by the product rule, times n2, and so on, up to nm. That's n times, and so on, m times, which is n to the m. Okay? So in this case, it's 6 to the 4. There's 4 times that we make a choice, and we have 6 options for each of those choices. All right. Yeah.
Is this like a for loop, basically? Like you start with an index 1 and it goes up to, but not including
Yep.
m?
Yeah. So when we use the product rule, we think algorithmically, and very often it's a for loop like this.
So wait, for loop goes up to but not including, is that true?
No, up to and including. So when I write things like this, I really mean all the values that I write down here. 1, 2, 3.
Because I thought like, I was thinking about up to including is like when the word Python and Java.
Yeah, in various languages, there's various ways to do this. In Python, if I said range m, that would give me 0 through m minus 1. But,
that is so
yeah.
I equals 1 to m including m.
Yeah.
Understood, let me write it down.
Yeah. So from here to here? Yeah, so this is a procedure that has m steps, right? That's what this loop is doing. M here is the number of elements in A. So for each element in A, we're going to pick what it maps onto in B. And when we do that, well, we get to pick anything from B. So we have n options for it. And, right, so the product rule says if we have a procedure and the number of ways to do the ith step is ni, then, well, the product rule tells us the number of ways to do the whole procedure. And in this case, the number of ways to do the ith step is just the number of elements in B. Doesn't matter what I is, and it doesn't matter what happened in the previous steps. Okay. All right, so far these were pretty easy examples. Let's try something just a little bit more difficult. So a function f from A to B is 1 to 1 if there is no pair x, y, so two elements of A, two different elements of A, such that f of x equals f of y. So that's what 1 to 1 means. So this example here, is it 1 to 1? No. Because f of A1 equals f of A3. They're both equal to 4. So this is not a 1 to 1 function. So this is not 1 to 1. And then the question is, how many 1 to 1 functions from A to B are there? And same setup as the previous question. Size of A equals m, size of B equals n. Here's A, here's B. Size of A is 3, size of B is 2. How many 1 to 1 functions are there from A to B? Yeah? In this example. 3 factorial? No. Yep. 0. So to see that, we can try and construct one of these 1 to 1 functions. In fact, if you were here for the bonus lecture on Friday, you know the answer to this. It comes from the pigeonhole principle. But if I'm trying to construct a 1 to 1 function, well, you know, first I'll pick something for A1 to go to over here. Then I'll pick something for A2 to go to. It has to be different from this one because otherwise I'm not going to get a 1 to 1 function. And then I want to pick something for A3 to go to over here that's different from the previous two, but there's none left. Yeah?
Can I make A3 just go to nothing?
No. No. So when you say a function like this from A to B, it means for every element in A, there is an element of B that's the value of that function. So in this case, there are no one-to-one functions in between these sets. So we'll put off to the side here. Answer is 0 if the size of A is bigger than the size of B. Right? We're going to run into this problem anytime we have more elements in A than in B. We'll just run out of elements in B. Okay. So let's go with a less trivial example. 4 elements in A, 6 elements in B. And the elements again are called A1, A2, A3, A4. And these ones are just called 1, 2, 3, 4, 5, 6. So can you describe me a procedure for making a one-to-one function? Yeah?
So you start at A1 and you have 6 possible options.
Yeah. So
And
let's choose something for A1. Let's say,
your number, and then at A2, you're left with only 5 options.
yeah.
So you multiply that out with the product rule. Then the next one, you have only 4 options.
Yep.
And then 3 options.
Perfect. Okay. So the procedure is the same thing, almost the same thing as before. For I equals 1 to m, you do the following. Choose a value bi in the set B minus f of A1, f of A2, up to f of AI minus 1. So this just says, just choose something you haven't picked before. And then you set f of AI equal to bi. So here, for example, for A1, I have 6 choices. So in this case, N1 is 6. For A2, I have any of these 1, 2, 3, 4, 5 possible choices. So N2 is 5. So let's pick one. And now for A3, it doesn't matter what I picked for A1 and A2. I know that I picked 2 different things. And so that means from the 6 things in B, 2 of them are not available to pick now, and there's exactly 4 left. Doesn't matter. I don't know which 4 left, but that's not what this thing, the product rule says. It just says, just tell me the number of options that you have right now. And in all cases, it's 4, no matter what the previous options were. So N3 is 4. We'll pick one of those. And finally, N4. There's only 3 of these things that don't have arrows coming into them. So I pick one. And so N4 is 3. Okay. So the answer here is 6 times 5 times 4 times 3 is 360. Sounds like we're dealing with angles here, right? No, we're not. Yep.
After you choose those values,
Oh, in the brackets here? Something you haven't picked before. It's just the, okay, yeah. It just says something you haven't picked before. So some people don't like this notation, bi and b minus the set of, this is the set of things you've picked before. So I just put a note here that, what does this mean in English? It means pick something in B that you didn't pick in one of the, oh, so let me write it out really big. bi in B minus f of A1, f of a2 all the way up to f of ai minus 1. Okay. This is the set minus notation. So take b, but take away all of the things that you picked in the previous steps. Yep. Not randomly, just saying here's a procedure for creating these one of these one-to-one functions, and it is from first element of A, pick something from B. Second element of A, pick something from B that's not the first one you picked. Third element, pick something from B that's not the first two you picked. Okay. So it's just a procedure, and there's a sort of a little bit of requirements to this procedure, a little more formal, but I think it's clear now. Any function I can generate this way, right? If you give me any one-to-one function from A to B, there is a way to generate it. It's look at that function, and then at step 1, you pick the value that that function has. Step 2, you pick the value that that function has for A2, and so on. And you also need to establish that if you execute the procedure two different ways, you get two different functions. And that's not hard, because if you execute the procedure two different ways, there's a first step where those procedures made a different choice, and therefore the function is different for that value, right? The function that this one makes is different than the function that the second one makes. Don't worry too much about that right now if you're not following, but this is a procedure that basically we can generate any of these one-to-one functions this way. Okay. All right. So let's write this down a little more in the general case. So what do we have here? We'll have ni. So we have I ranging from 1 through m. So in the first step, so n1 is going to be, that's when we choose for a1. We can pick any of the elements in B, right? So for n1 is just going to be n. Let's write that down. For n2, well, one of the elements in B was chosen in the previous step, so we only have n minus 1 ways to pick that. And for n3, we have n minus 2. So we can write this, see the pattern now, that ni is n minus I plus 1. Okay. Check for I equals 1. This is n minus 1 plus 1, so that's n. For I equals 2, it's n minus 2 plus 1, that's n minus 1, and so on. Okay. So, I'll just work here, because we don't have quite enough space for the answer on that board. So the answer is n times n minus 1 times n minus 2. And how far does this go? This is n minus, in the last step, I is equal to m minus m plus 1. Right? This is n1 times n2 times n3 all the way up to nm. Yeah? All right. And actually, if you think a little bit, if A is bigger than B, then that means we start counting at n, and we subtract 1, subtract 2, subtract 3, and so on, all the way up to subtracting m minus 1. That means one of the things in here is 0, right? Because we count down to a 0 or a negative number. So one of these things is 0, and this actually gives the correct answer for that case as well, because the product of all these things, one of the factors is 0, so it's 0. Okay, so it's not really a special case. Little sidebar, these kinds of products show up all the time in combinatorics. These products where you take, let's say, n, and then you multiply it by n minus 1, and you multiply it by n minus 2, by n minus 3. The sort of the most common of these, or the most useful of these, is when you do this all the way down to 1. So there's a notation for that. So for an integer k, k factorial is equal to k times k minus 1 times k minus 2, and so on, all the way down to 1. The only exception to this rule is if k equals 0, then we'll define k factorial to be 1. But otherwise, if k is bigger than or equal to 1, you follow this formula here. K times k minus 1 times k minus 2, and so on. And the reason we want that is we would like a shorthand for writing things like this down, so we don't write these long formulas. In the same way that when we have n times n times n times n times n times n, we can shorten that to n to the power m. Factorial lets us do this, and let's see how we would use it here. So what is this thing? It kind of looks like n factorial, right? N times n minus 1 times n minus 2, and so on, except it doesn't go all the way down to 1. Okay? So nevertheless, we can still use that. So that thing is equal to, you go to n minus m plus 1, and then keep going, n minus m, n minus m minus 1, all the way down to 1, and you do the same thing on the, all I did was take the thing on top and multiply it by 1. This over this is just 1, right? But, so why would I do this? Well, I do this because the thing on top is n factorial, and the thing on the bottom is n minus m minus 1, and so on. It's n minus m factorial. Okay. So there's the sort of concise way of writing that. So this factorial function is useful, even though factorial always counts down to 1. If you don't want to count all the way down to 1, you just divide by the number, 1 less than the number you're stopping at. Is that clear? Yeah?
That's permutation, right?
N factorial is the number of permutations. And so, in fact, if you take A and B to be the same size, then a one-to-one function from A onto B is a permutation. Everything in A gets to pick exactly one element in B, and everything in B is picked exactly once. Then what comes down here, this is 0 factorial, so it's 1, so you just get n factorial. Okay. So this is a generalization of the number of permutations. Okay. Yeah?
Does that formula work if the set B is Sorry, if m is greater than n?
If m is greater than n, so if the set A is greater than the set B, then this formula is not defined because we don't have anywhere a definition of factorial for negative numbers. And so it's not defined, but it's a good point that perhaps we should write out the theorem explicitly. Where are you? Here's a good place to write the theorem. The number of one-to-one functions from a set A of size M onto a set B of size N is 0 if M is bigger than N, or N factorial over N minus M factorial if M is less than or equal to N. Okay. So there is a case distinction there, which is actually a little bit of a drawback of using this factorial notation, because when we wrote it the long way like this, there was no case distinction. In the case where M is bigger than N, 0 appears in this thing, and the answer is 0. But that's okay. I don't think it's a named theorem. No. So, questions?
What's this n number of n binary string called?
The number of n-bit binary strings? What do you mean? What's the answer?
What's that about?
Yeah, I mean that. Oh, yeah. This is separate board. This was from the previous topic. I'm leaving it up there because the example is going to be useful again in a minute. Okay. So that's all clear to everyone? Good. So I said that there were going to be 2 rules that we discuss. And the second one is what's called the bijection rule. And actually, we'll see that we've kind of been using the bijection rule all along. Bijection from a set A to a set B is a function that is one-to-one. We saw what that means. And onto. What does onto mean? That means that every element of B, if you think of these arrow diagrams, is hit at least once. Okay. So the way to say that is for every y in B, or for each y in B, there exists at least one x in A such that f of x equals y.
So in the
What?
There exists one.
There exists some.
Okay.
Some means at least one. So what does that look like? So the first one says so the bijection has these two properties. It's one-to-one and onto. One-to-one means that if I look over in B, each element has only one arrow coming into it. Onto means that if I look over in B, each element has at least one arrow coming into it. So this function that I've drawn here, that's not onto because there's two counterexamples here. These are the y's, and I cannot find an x over here in B that maps onto those things. So here is an example of a function, a bijection from A to B. So what do you notice about this example? Yeah.
Every single A has something that correlates with B.
Yeah. They have the same size. So whenever there's a bijection from A onto B, that means that A and B are the same size. And that's just because, well, we already decided that you can't be one-to-one if B is smaller than A. On the other hand, if B is bigger than A, then you can't be onto because there's not enough things coming out of A to hit everything in B. So the only possibility then is that A and B are the same size. So that's the bijection rule. So not very exciting. Bijection rule, if there exists a bijection from A to B, then the size of A is equal to the size of B. And that can be useful to us because sometimes we know the size of some set A, and we don't know the size of some other set B, but for some reason that's problem specific, these two sets are related in a way and related enough that we can give a bijection from A onto B. And then we know that the size of B is the same as the size of A. What's really interesting about this one is it allows us, in some cases, to prove that the size of A is equal to the size of B, even if we don't know the size of A or the size of B. So sometimes we can determine that two sets have the same size, even if we don't know what that size is. And sometimes that's useful enough. Okay. So why do I say that we have been using the bijection rule? Well, because if you look at this product rule here, there's nothing about the product rule that talks about sets. It talks about a procedure, and it says the number of different ways of executing that procedure. On the other hand, we've been using it to prove things about the size of sets. So how has that been working? Well, basically we've been saying A is the set of ways of performing the procedure to create an element of B. And without saying it explicitly, we've been saying there's a bijection. from A to B. Right, if you think about this, the procedure for writing down n-bit binary strings was you write down the first bit, you write down the second bit, you write down the third bit, and so on. And there's 2 to the n different ways to execute that procedure. Now, if I execute it one way, and then I execute it again a different way, meaning that at some point I choose a different value, then I get 2 different bit strings. A different bit string from the first time, the first execution gives me a different one from the second execution. So that's what actually establishes the one-to-one aspect of this bijection, right? If I execute the procedure 2 different ways, in that case it means I write a different bit at position I. In one case I write a 1, in the other case I write a 0. Then I get 2 different bit strings. I know they're different because they're different at position I. On the other hand, I need to also show that argue that it's onto, and that means that for every bit string, there should be a way to execute the procedure so that I get that bit string. That's not hard to see because just give me an arbitrary bit string and I'll tell you how to execute the procedure to get that. You just write down the bits that you see in that bit string. That's the procedure, right? You pick the bit you pick is the one that's there in that bit string, so you certainly get that string at the end. Okay? So when you want to use the product rule, you should keep in mind, either explicitly or implicitly, that you're really establishing a bijection between the executions of the procedure you're describing and the objects in the set that you're counting. And sometimes the more common mistake is you mess up the one-to-oneness. So it's very easy to describe procedures where there's 2 different ways to execute the procedure that give you, let's say, the same bit string, or that, and you should go back and think about those examples we just did and make sure that really this is satisfied, that there's not 2 different ways to, if we follow the procedures we described, that there's not 2 different ways to get the same function, for example, or the same one-to-one function. You should check that. Okay. All right. So now for the most difficult example of the product rule.
What is, do you want to make from an exam?
Yes, this will be basically assignment 1 is all. The hard version, something like it could be. I mean, I won't ask you to from scratch solve a really hard problem that takes a bolt of intuition, but if that problem is almost the same as something I've shown you in class, then it's fair game. So here's the problem. We have M books called B1 to BM, and we have N shelves, so bookshelves, call them S1 to Sn. Picture looks like this.
Question.
Yep.
Can we use pigeonhole principle for this question?
You can use pigeonhole principle anytime you want, anytime it's applicable. So here's the picture. We have shelves, in this case n equals 3, and we have books, let's say B1, B2, B3, B4, and B5. And we want to place the books on the shelves. And we want to know how many ways there are to do that, where specifically what I care about is I care about the following 2 things. Which shelf a book is placed on, and also which order the books appear left to right on each shelf. Okay. I don't care exactly where the book is sitting on the shelf. Like, you know, if you put B1 here, right in the middle, or you put it over here on the all the way on the left, that's not two different placements for me. I just care, you know, it's different if you put B1 on shelf 1 or you put it on shelf 2. That really is a difference to me that I care about. And if you place more than one book on a shelf, then this B1, B2 is different than B2, B1. I call that a different placement. Yep. M. Good catch. Okay. So, question is, how many different ways? To place B1 through Bm onto S1 to Sn. Now, this is one of those ones that requires some real careful thought. It's not at all obvious how we're going to do this. So maybe it helps to start with an example. And another thing you can use is the fact that this example comes from a textbook, the same textbook that the other examples come from. And then, as you noticed, there's an M and there's an N in this question. And throughout this thing, M, or at least in the product rule, M is the number of steps in the procedure. So we can maybe guess then that whatever procedure we're going to come up with, it's going to involve placing book 1, and then placing book 2, and then placing book 3, and book 4, and so on. Okay? So, in this example with 3 shelves, to place book 1, how many options do I have? Yep. We have 3 options, because basically I'm just deciding which shelf to put it on. Okay. So in this example, N1 equals 3. So let's do that. We'll put it here. B1, we'll put it on shelf 2, and exactly where doesn't matter. Okay. Now, for B2, how many options do I have? Yep. I can put it on shelf 1, shelf 2, or shelf 3, but if I put it on shelf 2, I have 2 options, left or right of book 1. Yep. Yep. So that's the idea. Let's just convince ourselves that that's really what happens no matter where the books are placed. So here's the way to describe this. Here, let's say when placing BI, book I, it can go as the leftmost book on some shelf. So for book 2, it can go here, or it can go here, or it can go here. That's the sort of first class of options. Or, if it's not the leftmost book on some shelf, it can be immediately to the right of some book Bj for j in 1 up to I minus 1. Okay. So book 2, not only could it be the leftmost book on each of these 3 shelves, it could also go immediately to the right of B1. So that gives me 4 options now. And now I place book 2. Maybe I put it here, down on shelf 3. And let's just check that everything we said is true here. Now it's time to place book 3. Where can book 3 go? Well, it can go leftmost book on shelf 1, leftmost book on shelf 2, leftmost book on shelf 3. Or it can go immediately to the right of B1, or it can go immediately to the right of B2. And indeed, so those are 5 different options. Yeah? No, the shelves are long enough to, each shelf is long enough to hold all the books. Yep.
How many possibilities each shelf can have? Like shelf 1 can be like no book or 1 book, so 5 possibilities. 2 books, so we have to choose 2 of 5 and then place them.
Yeah, so it is, I mean, possible to grind through that way, but then you start looking at things like, okay, I have to choose which set of books goes on shelf 1 and then the order of those books, and then which set of books goes on shelf 2 and the order of those books. But just to choose which set of books goes on shelf 1, I have to choose, there could be no books on shelf 1, or there could be 1 book on shelf 1, or 2 books on shelf 1. But that's a problem if you're trying to think of the product rule, because if I put no books on shelf 1, then I have a lot more options for shelf 2 than if I put all the books on shelf 1, then there's no options left for shelf 2. So then it's hard to think of a way of writing a procedure where the number of options at each step is the same if you're doing 1 shelf at a time. And this is where sort of this lightning bolt comes in, where you can see a way to do it where you get exactly the same number of choices at each step. Yes?
Would you say using the combination
I don't know what the combination permutation rule is.
Factorial of how many options have over the
No. Maybe in that table of 6 things you might find, so here the books are distinct, the shelves are distinct, but I care about the order of the books within the shelves. So maybe I think there's a table usually of 6 things in the formula at each space. Maybe one of those applies here, but I would like to see how we can get to that thing. So you'll see why that formula is at that location. Okay, so then I place book 3, maybe it goes here. And now you see for book 4, it can go left, left, left. It can go after book 1. It can go after book 2, or it can go after book 3. So that's 1 additional choice here. Yeah?
So it seems like the pattern is every time you place a book, you gain additional possibilities.
Yeah. Yeah. So if we write this down a little more carefully, for the first book, we have number of options is just which shelf it goes on. But then after that, for N2, we have N shelves where it could be the leftmost one, or it could go right up beside book 1. And then N3.
N2 plus equals N plus N2 plus N plus 2 because it go left or right?
No, because if it goes left, then it's the leftmost book on its shelf. And we already counted that one.
Okay.
That's not a different option than the other thing. And you see, so there, when you think about it that way, you see, oh, you have to be really careful to really make a bijection from the procedures onto these things. Because if I said, oh, you can either make it the leftmost thing or you can pick a book and then go left or right, you see actually there's two different ways to execute that procedure where you get the same placement of books. So anyway, so that's the pattern, and that goes all the way up to the number of books is m. So this is n plus m minus 1. So that product rule says n times n plus 1 times n plus 2 all the way up to n plus m minus 1. And so we don't have to do this in the longhand way. We can write this in terms of factorials. So if you look at this guy, it starts at n plus m minus 1, and it counts backwards, minus 2, minus 3, minus 4, all the way down to n. And if we kept counting, we'd go all the way down to 1. So let's put that n plus m minus 1 factorial up there. But we don't really have this n minus 1, n minus 2, n minus 3, and so on. So let's kill that with n minus 1 factorial. Or not, one of the formulas will be this one. And this is where the items are unique, distinct, the shelves are distinct, the boxes are distinct, and you care about the order within the boxes. Okay. Questions about that? Yep.
Where does the minus 1 come from on n plus n minus 1?
Because we start with n1, n, and 2 is 1 plus 1, and 3 is plus 2, and we get all the way up to nm. Well, this isn't, ni is not equal to n plus I, it's n plus I minus 1. Yeah. Yes?
I don't really understand why you did n minus 1.
Let's write this long way. N plus m minus 1, n plus m minus 2, all the way down to n, and keep going, all the way down to 1. So this thing here, that's this thing, right? It's just writing it the other way around, okay? So I multiply that thing by this. So now on the top here, this is n plus m minus 1, counting all the way down to 1. That's n plus m minus 1 factorial. And this thing on the bottom is n minus 1, n minus 2, all the way down to 1. That's n minus 1 factorial. Yeah. You'll quickly get used to working with these things. It becomes second nature. All right, that's it for today.
Yeah, it's kind of took the chance. I thought you were about wrapping up. Just a quick, silly question.